Hello everyone, I am Dr. Naresh Kumar, Assistant Professor from the Department of Electrical and Electronics Engineering, Institute of Aeronautical Engineering, Hyderabad. Today we are going to have a discussion on inverter numerical problems. So here total 26 questions from the gate point of view. So first question is here a single phase full bridge voltage source inverter feeds a purely inductive load. So as shown in the figure, so this is the figure. So in this T1, T2, T4, T3 and T4 are power transistors, and D1, D2, D3, D1, D2, D3 and D4 are feedback diodes. And the inverter is operated in a square wave mode with a frequency of 50 Hz, and the average load current is 0. And what is the conduction time? So what is the time duration for conduction of each feedback diode in a cycle? So here this is full bridge voltage source inverter. In the full bridge voltage source inverter, so this is the voltage source inverter, this is the output voltage and V0. So now here what about the current? So here current waveform, here the current waveform is triangular. So now here this is pure current waveform is triangular. So this is a triangular. So now here each diode is conducting for T by 4 duration. This is total time period T. So this is T by 2 and next this is T by 4 duration. Each diode is conducting for T by 4 duration. So now here total time period is T by 4. Here T by 4 means here what is the 4? This is the 4. So 1 by 50. 1 by 50. T by 4. So that equals 1 by 4 F, that equals 1 by 4 into that is 50. So that means 20 into 10 power minus 6. 10 power minus 3. So 5 milliseconds your answer. And next second question is in a figure as shown in the figure. Inverter circuit with voltage DC source, so that is Vs. So what is the this is a supply voltage Vs, source voltage. The semiconductor switches of inverter are operated in such a manner so that the pole voltage V1 0 and next V2 0 as shown in the figure B. This is figure B and this is figure A. So what is the RMS value of pole to pole voltage? This is pole voltage V1 0 and pole voltage. So V1 2 equals to V1 0 minus V1 2. So now this is a V1 0 and this is a V2 0. What difference is the phi? So now here this is a V1 0 and this is a V2 0. There is a difference. So that is phi. So here the conduction time of these thyristors, that is phi. From this phi duration, from the pulse width modulation, we can determine the RMS value. That RMS value equals to that phi. So that phi duration, it is conducting for. So that is we know this very well. So Vrms equals to Vs into square root of phi by this phi by pi. So up to pi, this phi duration it is conducting. So here up to pi and this phi duration it is conducting. And next here third question. So with the reference to the output waveform in a given figure, what is the figure here? So this is the figure. So what is the converter output voltage will be free from fifth harmonic. Fifth harmonic means here. Fifth harmonics means here to eliminate fifth harmonic here 0, pi, 0, pi, 2 pi. So these are the harmonics here, fifth harmonic. So now here D equals to 0 by 5 and pi by 0, pi, 2 pi, 0 by 5 and pi by 5 and 2 pi by 5. So pulse width 2D equals 0 by 5, 2 pi by 5 and pi by 5. So 2D equals to 0 by 2 pi by 5 means that is here 72 degrees, 144 degrees, 0 degrees. So now here next question. So an inverter has periodic output voltage with the output waveform as shown in the figure. So same figure as shown in the previous problem in the question number 3, when conduction angle is 120 degrees, that is alpha. So now here RMS output voltage, fundamental component of RMS output voltage is here. So now here alpha equals to 120. So this is 120 degrees. That means 2D equals to 120. 2D equals to 120. So now here RMS output voltage equals to, that is here 2D. This is 2D equals to 120 degrees. So now here Vs into square root of 2D by pi. This is your here how we will get 2D equals to 120. So now here 2D equals to 120 and D equals to 60. So now here RMS output voltage equals formula, actual fundamental voltage equals to RMS value of fundamental. This is the Fourier series of output voltage. So sigma n equals 1 to 3 and infinity 4 Vs by n pi sin nd sin n5 by 2 sin n by 2. So now here substitute n equals to 1. So that is fundamental, and by root 2, whatever the output voltage, by root 2 is the RMS value. RMS value of fundamental component means here substitute n value equals to 1 and sin pi by 2 means that is 1, and now here 4 Vs by root 2, that is RMS value sin D into A. So now here not this A. And now here D equals to 60, and now here your output voltage equals to 0.78 volts, not Vs, not volts, Vs. And next here fifth question is, a single phase inverter is operated in pulse width mode, generating a single pulse width 2D in the center of each half cycle as shown in the figure. So this is the figure. So this is the pulse width. So now that is 2D in the center. So that is pi by 2. So now it is found that output voltage is free from fifth harmonic for the pulse width is 144 degrees. So pulse width is 144 degrees. So what will be the third harmonic percentage in the output voltage? Output voltage means here that is, so V03, third harmonic by fundamental harmonic in that maximum voltage. So first calculate the third harmonic component output voltage and fundamental component of output voltage. So now here we know the very well formula. So that is from the Fourier series equation, 4 sigma n equals to 1 3 5 infinity 4 Vs by n pi sin nd sin n pi by 2. So that is substitute in that. So n equals to 3. So sin 3 pi by 2 is 1 sin 3d and 4 Vs by 3 pi. And this is the fundamental 4 Vs by n value is 1 and n equals to 1. So now here Vs gets cancelled. Here d equals to 144. So 2d equals pulse width equals to 144. So now here from this you will get 19.6. And next here, sixth question, a single phase voltage source inverter is controlled in a single phase, single pulse width modulated mode with a pulse width of 150 degrees. So 2D equals to 150 degrees in a half cycle. So third harmonic distortion. So the definition of third harmonic distortion is equals to square root of Vrms square minus V1 square, that is fundamental, by this is V1. So now into 100. This is the THD. So total harmonic distortion, where V1 is the RMS value of fundamental component of output voltage. So now calculate this THD output voltage, AC output voltage. So now here how we will calculate the RMS value and fundamental value from this 2D. So now here 2D, this is 2D. So that 2D equals to 150. So now here 2D equals 150 means D equals to 50. So now here RMS value, this RMS value how you will get? So now that VRMS equals to, so Vs by, so from this Vs by, so that equals to here 2D by pi. So that equals to Vs into square root of 2D means 150 by 180 into Vs, that equals to 0.9135 by 6. So that is 0.913 into supply voltage. Now here this is a Fourier series equation. So from this Fourier series equation, so now here you can calculate the fundamental output voltage RMS value. This is by root 2, that is you will get the RMS value, and here substitute this n equals to 1 and this n equals to 1, D equals to pi by 2, and now here this value equals to 0.87 Vs. So now here this is 0.913 whole Vs whole square minus 0.87 Vs whole square by 0.87 Vs whole square. So that is the 31.83 percentage. So this THD value. And next, seventh question is a single phase voltage source inverter is feeding purely inductive load. So now here the inverter is operated at 50 Hz in 180 degrees conduction mode, as shown in the assume that the load current does not have any DC component. So now calculate the peak value of inductor current. So now here this is 180 degrees conduction mode means it is T1, T2, T3 and T4. This is supply voltage Vs. So this is 200 volts. This is purely inductive load. So this one. So now here peak value. So if you know this output voltage waveform, this is the output voltage waveform. So during the 0 to T by 2, so T1 and T2 thyristors will conduct, and this negative off cycle T3 and T4 thyristors will conduct. And next here it is a purely inductive load means here. So D1, D2, D3 also will coming to the picture. And next here, what is the peak value? So here this is the current waveform for pure inductive load. So here for pure inductive load, what will happen? So actually V0 equals to DL by DT. So we know very well this formula, V0 equals to 200. But here this L value is given 0.1, and next di by dt means this IP minus IP and T1 minus T0. So from this you will get the IP value. So now here this I0 value equals to pi by, so T1 into pi by, T1 is equals pi by omega. So this pi by 2 pi, this pi, this one equals to 50 hertz. So now 2 pi f. So omega equals to 2 pi f. So now here substitute this time in this, you will get the peak value, that is 10 amperes. And next question, 8th question, the current source inverter as shown in the figure. This is the figure. This is current source inverter. In the current source inverter, the output current is constant. Output current is constant, and output voltage is depending upon the load only. So now the current source inverter is operated by alternately turning on thyristors T1 and this is T1 and T2. So where is the T2, T1 and T2? So this is and next to T3 and T4. This is T3 and T4 is if it is purely resistive. This is R load. So now the theoretical maximum output frequency. So there is a formula. This is the formula 1 by 4 RC. So that equals to, this is the R and this is the C value. So what is the C value? 0.1 into 10 power minus 6. So now here the frequency value is the maximum output frequency value is the 250 kilohertz. And next here, ninth question, a three-phase inverter as shown in the figure. So this is three-phase inverter, three legs over there. So upper switches are odd group. So S1, S3 and S5, and S4, S6 and S2 are the lower group switches, that is negative group switches. And the load is balanced, that is balanced means this is 20, this is 20 and this one is at 20. It is in 180 degrees conduction mode. All the switches, devices are ideal switches. These are all these switches are ideal switches. Now calculate the RMS value of output voltage. Direct formula is here. So that is root 2 by 3 Vs. So this is we got from the line voltages waveform. So now here root 3 2 by Vs. So thus this Vs equals to this with root 2 by 3. So now here therefore RMS value of load phase voltage. This is line voltage. What about the phase voltage? Phase voltage means this line voltage by root 3. We know very well this formula. Phase voltage equals to always line voltage by root 3. We have already studied in the three-phase circuit. So phase voltage equals to line voltage. So root 2 by Vs by this root by root 3 means here root 2 by 3 Vs. So now here Vs value is here 300 volts. So this Vs value equals to 300 volts. So this value root 2 by 3 that equals to 141.4 volts. And next here same question. So in the previous question VD was not given. And next that same question but two questions in the same question. In the three-phase inverter same diagram. So this is 20, 20 and now here 180 degrees conduction mode. So calculate the power after getting phase voltage. So now here that is 1.41 in the previous question, ninth question. So 141.4 whole square, that is phase voltage square by R. So this 141.4 whole square by 20, that is 1000 watts. So it is a three phase means total power consumed is here 3 into P, that is this is 1 kilowatt. So this is 3 kilowatt. And now here 11th question, the voltage source inverter as shown in the figure switched to provide 50 Hz square wave AC output voltage, that is V0. Here we RL load. So here the diagram is this is the RL load. So now the polarity of V0, the reference direction of the output I0 are indicated in the figure. So the given R value and L value. R is given that is 3 ohms and L is given that is 55.9 milliohms. So now appropriate transition, that is zero voltage switching, that is ZVS, zero current switching, that is ZCS of IGBTs. These are the IGBTs during the turn on and turn off. So now here, so ZCS is turn on in this case. So here zero current switching is turn on. So here four possibilities: ZVS turn on and turn off, and ZCS turn off and turn on. Here ZCS is the zero current switching is turn on. And next to second question is the, so at what interval when in the interval V0 is less than and I0 is greater than. So now this is the full bridge inverter. So now here it is a RL type of load. So now in the RL type of load, voltage is negative and current is positive, means in that case voltage is current is positive and voltage is negative, means in that case D3 and D4 will conduct. Already we have studied in the full bridge inverter with RL type of load. So in the 0 to some duration, so in the positive voltage source, negative positive current and negative voltage, so which diodes are conduct, so that already we discussed. And next 12th question, So in the figure, this is the figure. So shows one period of output voltage. Here is there any output? One period means here. So up to 360 is one period. Not up to here, this is one period. So here this is negative. So this is negative, but this width is different, these two. So it is up to 360 is one time period. Time taken to complete one cycle is known as the time period. So what about the cycle? Here cycle means complete set of positive cycle and negative cycle. So here these positive sets and negative sets that is one cycle. So now here output voltage is here, output voltage equals to, but here they were given here RMS output voltage that equals 50 root 2. So now this is 50 output voltage, that is 50 root 2 means RMS output voltage. First, what about the output voltage? That is sigma n equals to 135 infinity an cos n omega t plus bn sin n omega t. So now if you expand this one an, bn, so now here an equals to 1 by t by 2. So that is 2 by 2, 0 to t, f of t cos omega t. And what about this bn equals to 1 by t by 2, that means 2 by t, 0 to t, f of t sin dt. So for an this is cos omega t and for bn this is sin omega t. So now first in the an, number of intervals in the up to 0 to 360. So now first 0 to alpha, what is the value? 100 from 0 to alpha, and alpha to 180, that value is minus 100, and next 180 to 180 plus alpha, sorry 180 minus alpha, and 180 minus alpha to 180, that is 100, and 182 and 180 plus alpha, that is minus 100, and next 180 plus alpha to 360 minus alpha, that is 100, and next 360 minus alpha to 360, so that is a minus 100. Same way here for bn is also, so 0 to alpha, alpha to 180, 180 to 180 plus alpha, so 180 minus alpha to 180, 180 to 180 plus alpha, 180 plus alpha to 360 minus alpha, 360 minus alpha to 360 according to the diagram. So now here this bn equals to, so now here this is the 50 vs by pi by 2. So now here this one equals to, if you simplify this one, bn equals to 100 by pi. So the simplification is here minus cos, if you integrate is minus cos alpha plus 1 plus cos 180 minus alpha minus cos alpha minus cos 180 plus cos 180 minus alpha, cos 180 plus alpha minus cos 180 minus cos 360 minus alpha plus cos 180 plus alpha, cos 60 minus cos 60 minus alpha. Just integrate this sign, you will get the minus cos alpha cos 0 to alpha. Substitute that interval, you will get this one. And next here bn equals to this one, the simplification is this one. So after this is our given RMS fundamental voltage, that is 50 is given, that is 50 root 2. Now this value equals 50 root 2. If you solve this one, you will get the alpha equals to 77.15. And now here 13th question. So a single phase full bridge voltage source inverter, that is VSI. So the diagram is, so here 4 thyristors and 4 diodes, and it is having output frequency is 50 Hz, and the unipolar pulse width modulation with switching frequency is 50 kHz, and the modulation indexing is 0.7. In the previous questions there is no modulation index. Here another extra term is modulation index. In the upper output RMS voltage, you can multiply that modulation M equals to 0.7. For V input equals to 100, and this L equals to 9.5 millihenries, and this C equals to 63.66 microfarads, and this R value equals to 5 ohms. The amplitude of fundamental component in the output voltage V0. So here how you will get amplitude of output voltage. So first here what you will do, this is important, RMS value of fundamental component of output voltage. So that is formula. So supply voltage by root 2 is the RMS value, but here another word is given, modulation index. So modulation index is always multiplied. So that is 100 by root 2 into 0.7. So now peak value means 100 into 100 only, 100 into 0.7, that is 70. So for this into root 2, that is 70. And next here, so now here how you will calculate the impedance. So Z equals to, so here this C, XC and R are connected in series. So now here XC or what about XC? XC equals 1 by omega C. Omega equals to 2 pi F. F equals to 50 Hertz. And next C equals to 63.6 into 10 power minus 6. And next XL value, this is XL equals to same 2 pi F into omega L. L equals to 9.55 millihenries. So now here we need here output amplitude of fundamental component in the not RMS value, here peak value of RMS. Peak value, how you will get this peak value? So now here this Z equals to Z equals to this R into this minus ZXC. So now if you simplify this XC means, so now this 5 is R value and XC value is minus J, XC by 5 plus. So these two are connected in parallel. So this is your impedance. From this impedance, you can calculate the peak value of voltage. So now here this is reactance, that is J3, and this is the voltage. So now here voltage peak output voltage equals to this peak voltage into this impedance, inductive reactance. So plus this one, this you will get here 62.75 at an angle of minus 32.5. And next here 14th question. So the switches T1 and T2 in the figure are shown in the figure complementary fashion. So sinusoidal pulse width modulation technique. So now here V0 equals to 0.8 sine 200 pi t volts. The triangular carrier frequency is given and in the figure 2. So this is your half bridge inverter, 2 switches. Okay, now this is a RL load. So carrier frequency is given 50 Hz. So the peak value of 100 Hz component of load current. So now here you will get, so now here this is the modulation index. So now M equals to, this is modulation index in the figure B is given 0.8. So now peak value equals to this is the Vd by 2. So 0, 1 equals to output voltage equals to Vs by 2. So thus that is Vd by 2, Vdc by 2. So Vdc by 2 means that is 250. So another word is extra comes here, that is modulation index. Actually this is for 1 and this is the modulation index. So multiply 0.8, you will get the 200 volts, that is fundamental component of peak value. And next to that peak current equals to divided by Z. Z means equals to R plus J XL. So this is take modulus and square root of 12 square plus 16 square. So finally you will get the 200 by square root of 12 square plus 16 square. So that equals to 10 amperes. A single phase full bridge voltage source inverter is fed from 300 volts battery. A pulse of 120 volts duration is used to trigger the appropriate devices in each off cycle. So the RMS value of fundamental component of output voltage is in, so now here, so we know very well this one. So now sigma n equals to 135 infinity 4 Vs by n pi sin n d by sin, so n pi by 2. So this we know very well. So now here n equals to 1. So 1 means here fundamental component. So n value is 1 and by root 2 means that is RMS value. So now here 2d equals 120 means d equals to 60. So now here 4 Vs by root 2 means 2 root 2 by pi, there is a pi Vs, and next sin d. So this is your fundamental component of RMS output voltage 2 root 2 by pi Vs sin d. So now sin d equals substitute 60. So now here substitute 60 means here you will get the 230 volts. So now here this Vs equals to 300. Next, a three-phase voltage source inverter as shown in the figure is feeding a delta connected resistive load of 30 ohms per phase if it is fed from 600 volts battery with 180 degrees conduction of solid state devices. The power consumed by the load. So already we discussed a similar type of problem. So this is balanced type, but in the previous session we discussed about delta connection. So now here balanced delta connected load. So this equals to root 2 by 3, that is line voltage. But in the previous problem there is a star connection. Star connection, line voltage equals to phase voltage equals to line voltage by root 3. But in the delta connection, line voltage equals to phase voltage. That phase voltage equals to square root of root 3 by 3 Vs in case of 180 degrees conduction mode. This is the formula. This we got from the output voltage waveforms. So now here phase voltage equal root 2 by 3. This voltage waveform, this equals to 600. So this one equals to 600. So now after getting this one, this value root 2 by 3 into 600, this is V phase. So substitute this V phase and you will get the, so 3 multiplied with 3. So now here this is your power consumed by the load. So that is 24 kilowatts. And next, a three-phase voltage source is supplied from the 600 volts. Supply voltage is 600 volts as shown in the figure. Same three-phase, but it is a the load power is 120 degrees conduction mode. This one, not 180 degrees conduction mode. Star connected load. So that, but it is a balanced load. So same type of problem, but it is a 120 degrees conduction mode. But that that this is output voltage waveform, phase voltage waveform, and now here this is RMS output voltage equals to, so that equals to pi gets cancelled. So same root 2 by 3. So that is Vs. So that is V, that equals to 600. So now, so I think this is 600. Now here this is 244.94, and now multiply what about this Vrms square 3 into this Vrms square by R, that is power consumed by the load. 600 by 2 to 1 by root 3 I think. So this is 1 by root 3. And now here 18th question, and circuit, converter circuit as shown in the below. The switches are controlled such that the voltage, load voltage V0 is 400 Hz square wave. The RMS value of fundamental component of voltage V0, V of T in volts. So this is full bridge inverter T1, T2, T3, T4. This is the load. So now here how we will calculate? So that voltage is 400 volts, 400 Hz here given. So now we need only this voltage only, 220 volts. So now here 4 VDC by, so same 4 Vs by n pi sin nd sin n pi by 2. So here n equals by root 2 means RMS value, 1 means here fundamental component. So now RMS value, fundamental component of output voltage. So 4 VDC by root 2 by pi. So that equals to 2 root 2 by pi. So here VDC equals to 220 volts. So finally you will get 198.06. And next question. A 3-phase voltage source inverter with ideal devices operating in 180 degrees conduction mode is feeding a balanced star connected resistive load. So now the DC voltage source is VDC, the peak fundamental component of voltage. So this is 180 degrees conduction mode. So now here what about the this voltage equals to, so 6 VDC by 3 n pi sin n omega t, n equals to 1 means that is fundamental, and now here 2 VDC by pi sin omega t, so that VRN equals to 2 VDC by pi, so 3 into 2 VDC by n pi, so that one. 20 question. So in the figure, what is the figure here? So single phase of bridge inverter. So S1 and S2 VDC and VDC by 2 VDC, and now here our bridge inverter supplying RL load with R value is 40, this is 40, and L value is 0.3 by pi H, and the desired fundamental frequency of load is 50 Hz. The switch control signals of converter are operated using sinusoidal pulse width modulation index is 0.6. At 50 Hz, the RL load draws an active power of 144 kilowatts. So the value of DC voltage source. So now here peak output voltage equals to modulation into this VDC by 2. So now here this VDC by 2 means Vs by 2 means here. So now here what about 0 m value is given. So now here Vs by 2 by root 2 means that is 2 root 2. So this is m equals 0.6 Vs by 2 root 2. So now here how we will calculate. So actual formula is active power is here, active power equals to how we will get the VDC. Here we need VDC. VDC how we will get. So V01 I01 cos phi. So V01 I01 Z1 by cos phi. So now here Z1 can be calculated from this. So Z1 equals to Z1 and phi value. Phi value also calculated from this load omega L by R. L value is given. So that is omega L by R. 2 pi f by R value is 40 and omega 2 pi f omega L value 2 pi f value into L. So that is 30. So now here impedance is 50 and this angle is this much. So now here we know very well about this V01 and next this impedance and this cos phi. And next what about this active power equals to this much 144 kilohertz. So from this you can determine Vs. So Vs equals to this Vs equals to VDC equals to Vs by 2. So that value equals to 500 root 2. The output voltage of single phase full bridge voltage source inverter is controlled by unipolar pulse width modulation with one pulse of off cycle for fundamental RMS component of output voltage to be 75 of DC voltage, the pulse width of the degrees. So now we know very well in the full bridge inverter. So that equals to root 4 Vs by 5 root 2 pi. So that is this much. And now here this value 4 Vs by 2 pi means that value is 0.9. So this is 0.75 into Vs. So now here from this you can determine D value. So Vs gets cancelled. So this is Vs. And now here D equals to 112.88 degrees. That is pulse width. A single phase full bridge inverter is fed by 325 volts DC. Gives a systematic Kasai square waveform across the AB terminals. So across this AB terminals, as shown in the figure. So to achieve a modulation index, that is 0.8. So now here calculate this theta value. This value we need. So first calculate that angle. So that pulse width 2D value first calculate. From that calculate the theta value. So now here V01 equals to M into Vs. So M is given 0.8 and Vs is given 325, that is 260. So now V01 equals to 4 Vs by pi sin D is equals to 260. So now here from this D value is calculated, that is 38.9. So now here this is exactly off. So now here this is D and this is D. So now here pi by 2 minus D means that is theta. So that is 51.1. 23. A three-phase grid connected voltage source converter with DC link 1000 volts is switched using sinusoidal pulse width modulation technique, that is PWM technique. So if grid current is 10 amperes, so the three-phase complex power supplied by the converter is, so this is complex power is given. So this is P and Q, P plus JQ, and then the modulation index. How we will calculate the modulation index? So after getting the output voltage, peak value of output voltage you can get easily. But here what is the apparent power equals to? So complex power AC equals to root 3 VL IL. So first calculate this VL root 3. IL value is given, that is 10 ampere, and next that is root 3, and this S value is given, that is 5000 at an angle of. This is in polar form, convert into the rectangular form, convert into the polar form. So that is 5000 at an angle of minus 143.13. So now here, so after getting this one, so now here you got this P01 equals to root 3 Vs by now here this peak value equals to root 3 into, this is the modulation index Vs by 2. So now here substitute this one. So this one equals to 288.675. So from this you will get the MA value equals to 0.471. Consider a full bridge single phase DC to AC inverter with DC bus voltage magnitude of 1000 volts. The voltage source inverter as shown in the figure, it is obtained diagonal switches of inverter are switched 50% of duty cycle. So the inverter feeds a load, sinusoidal load. This is the equation I of t, equation 10 sin omega t minus 10 pi by 3 amperes. Omega equals 2 pi by 3. Calculate the active power delivered to the load. So this is a V01. So 2 root 2 by pi, that means 4 Vs by root 2 pi. So now here after getting this V01, active power equals to V01 IRMS and cos pi. So pi value is given, that is pi by 3. So now here this is the pi by root 2. So pi by root 2. So finally 3.183 kilowatts. And next here 25th question, a single phase half control bridge converter supplies an inductive load with a ripple free load current. The triggering angle of converter is 60 degrees. The ratio of RMS value of fundamental component of input voltage, input current to the RMS value of total output current. So now here this is the diagram. So here T 2D equals to pi minus alpha. So now here pi value is given, that is pi by 3. So now 2D equals to, this is pi by 3. 2 pi by 3. So that is 120 degrees. So now G equals to 3 pi, G equals to pi by 3. So now here G equals to IS1. So now not this one. So this is, so G equals to IS1 by IST. So that is 2 root 2 pi by I naught cos alpha by 2. So now here I naught pi minus alpha by alpha under root. So now here you will get, so this is under root. So now here I naught gets cancelled. So now here alpha value you substitute. Finally you will get a G value equals to 0.955. So now the last question. A single phase full bridge voltage source inverter feeds a purely inductive load. So the inverter output voltage is quasi waveform in the 180 degrees conduction mode. The fundamental frequency of output voltage is 50 Hz. If the DC voltage, input voltage, inverter voltage is 100 volts and the value of load inductance is 20 millihenries. The peak to peak load current is appears. So this is peak to peak current means already we discussed. So Vs equals to L di by dt. So now here Vs equals to L. So I minus I by this peak to peak Im minus of Im by dt. So here from this that value equals to Im equals to 4 Vs by 4 Fl. F value substitute and next L value substitute. L value is given and now here Vs value is given 100. So now your peak to peak current is 50 amperes. I hope all these problems are clear to you. If you still have any doubts in this lecture, you can comment in the comment section below. I will answer to your queries. Thank you very much to you all.
Like, share and subscribe. Hit the bell icon for more updates.